Welcome to the first chapter of the Pragmatic REST APIs course, where I'm going to introduce you to the concept of REST. This chapter is going to serve as a foundation for the remainder of this course, where we are going to cover the basics of REST from a practical and theoretical standpoint, and we're also going to create the building blocks for the application that we'll be creating throughout this course. Here is a quick overview of what we will cover in this chapter. First, we will cover what REST is, and we are going to introduce and explain these 6 REST constraints and what impact they have on the REST architectural style. Then I'm going to introduce you to the Richardson Maturity Model, which gives us a way to measure how RESTful our API actually is. After that, I'm going to introduce what we will be building inside of this course to demonstrate the concept of RESTful APIs in an ASP.NET Core application, and we're also going to be introducing a user interface to add another dimension to this course. And in the final lesson of this chapter, we are finally going to write some code and set up the project that we are going to be building throughout this course. We're going to cover some of the best practices like setting up build configuration, package management, observability, containerization, and we're going to set up a CI/CD pipeline. And with that, we can conclude this introductory lesson and we can move on to the next lesson in this chapter, where I'm going to introduce you to the concept of REST. Welcome to the next lesson in this chapter, where we are finally going to explore the concept of REST and understand what it means. And the first obvious question that we should ask is, what is REST? REST is actually an acronym, and it stands for Representational State Transfer, and even though it may seem confusing at first, I promise that by the end of this lesson you will understand why it's called representational state transfer. But let's start with a bit of history. REST, as we know it today, was actually introduced all the way back in the year 2000 by Roy Fielding inside of his PhD dissertation. The title of his dissertation was Architectural Styles and the Design of Network-Based Software Architectures. And inside of this dissertation, there is a chapter called Representational State Transfer, where Roy Fielding introduces this architectural style and the constraints that you have to accept in order to implement REST correctly. Now, I want to make some initial remarks from my experience of building RESTful APIs before we move on with this lesson. First, I'm going to use the terms REST and RESTful interchangeably because they essentially mean the same thing. There really isn't any difference between a REST API and a RESTful API. Second, as with many historical examples in software development, patterns and principles tend to take on a life of their own, and REST is no exception. So over the years, REST has evolved to mean many different things. Inside of this course, we are going to discuss Fielding's definition of REST, what it is and how you can implement it, and I'm going to tack on a dose of pragmatism from personal experience, which sometimes may be in conflict with the REST principles, but nonetheless the end result is going to be a very high quality and usable API. So let's move on with the definition of REST. Here is a definition of REST from Fielding's dissertation, where he says that representational state transfer is intended to evoke an image of how a well-designed web application behaves. It is a network of web pages or a virtual state machine where the user progresses through the application by selecting links which represent state transitions. And these state transitions result in giving the user the next page, which represents the next state of the application, and this is transferred to the user and rendered for their use. Now, I highlighted a few key phrases here. First, there is the network of web pages, representing the actual resources that your application server is exposing to the user. Then we have links, which represent state transitions, but are essentially hypermedia controls, allowing us to navigate through the available resources. And then there is the state of the application, which is being transferred to the user in some form that can be rendered on the user interface. This could be HTML, it could be XML, it could be JSON, it doesn't really matter. What's essential is that it represents the state of the application in a representation that can be rendered for the user. So let's try to understand this with an example. Let's say we have a browser representing the user interacting with the REST API server, and the browser sends a request to the server that contains some resources. This communication uses the HTTP protocol, and the browser requests a resource with this URL. This is the specific URI of the resource. It's article 1, where URI is short for Uniform Resource Identifier, and then this is the host address where the server is available. The server is going to take this request and is going to send a response to the browser, which is going to render this response to the user. And this represents the current state of the article 1 resource. Now we can expect that somewhere on this page there is going to be a hypermedia link allowing the user to navigate to another resource, another article on our blog. And this would result in sending another request for another resource, let's call it article 2, which is another web page on our server that we would transfer back to the browser or to the client in the response of the HTTP request, and we're going to render that on the screen, and then the cycle continues. Now we can easily extrapolate this concept to a REST API. Instead of sending a request to access a web page, we want to access one resource on our REST API server. We get a response back in JSON, which is the current representation of this resource, and this resource is going to contain a set of hypermedia links allowing us to interact with this resource. The hypermedia links are going to drive the application state and tell us what are the available operations that we can execute next. Here are a few more remarks about REST. REST is not a standard, even though sometimes it's considered as such. It's actually an architectural style. And an architectural style is a named set of constraints that produce some specific properties. So we are going to introduce the REST constraints next, explain what they are in detail, and try to understand what are the specific properties that each constraint introduces, and what are some of the trade-offs that we are making in order to implement a specific constraint. But before we jump into that, I want to discuss some alternatives to REST APIs. REST isn't the only way to implement communication through HTTP. For a long time, a popular approach was the SOAP protocol, which uses XML payloads sent over HTTP to implement communication between clients and servers. In more recent times, we have gRPC, which uses a binary message format to implement communication. Then there is also GraphQL, which aims to solve some of the drawbacks of REST. And there is also OData, which is an approach to standardizing REST. Now, just a heads up that I won't be diving into the alternatives too much, but I am going to leave some useful resources if you want to learn more, and they're going to be right under this video. Now let's move on with this lesson. And the next big topic that we have to cover is understanding the REST constraints. As I said, there are 6 REST constraints, and the first one is the client-server constraint. Then there is the stateless constraint, the cache constraint, also called cacheable. There is the uniform interface constraint, which is the most complex one, and it consists of several sub-constraints. Then we have the layered system constraint and the code on-demand constraint. Now let's tackle them one by one. The first REST constraint is the client-server architectural style. We are going to split our system into the client application and the REST server. The server may interact with a database, but essentially it's going to expose a set of REST API endpoints that are going to allow the client application to interact with the REST API server and retrieve the available resources in order to render them on the client, and also trigger any actions that are going to manipulate the state of these resources. So what do we stand to gain by accepting the client-server architectural style? First of all, we are separating the client application and its concerns, which involve dealing with resources and their representations, rendering them on the client, and invoking the operations that are available for a given resource in order to manipulate the state of that resource on the server, from the server-side concerns that deal with managing these resources, interacting with the database, exposing the RESTful APIs, and so on. A big benefit of the client-server architectural style is that it allows us to independently evolve the client-side application from any server-side components. We have the ability to introduce new components on the server, maybe remove old or legacy components, and even switch some implementation details, and all of this shouldn't affect the client application so long as we respect the RESTful API that we are exposing. However, a drawback of this constraint is that we now need to make a network request between the client application and the server application. This introduces latency, and it also introduces some security concerns that we're going to solve in a later chapter in this course. The next constraint is the stateless constraint, which states that all communication between the clients and the server has to be stateless. Now this has some interesting implications. So let's say all communication is now stateless. What does this actually mean for our system? are we no longer storing any state on the server? What about the database? What happens to that? Well, the stateless constraint actually deals with how we interact with our API. Each request has to contain all of the information that is necessary in order to process this request. In other words, we aren't storing any session state on the server which is specific to a given client. And this constraint gives us a few interesting properties. First of all, the visibility inside of our system is improved because all we have to do is to look at a single request to be able to understand what is currently happening because each request contains all of the necessary information. Secondly, this makes our system more reliable because we are able to retry failed requests as they contain all of the necessary information in order to process it. And another advantage is improved scalability because of the fact that the server doesn't have to store any state in order to interact with a client. This gives us the ability to scale out our REST API into multiple API instances, and all of them are now able to accept and respond to client requests. The stateless constraint also introduces a trade-off, and this is decreased network performance, and this is because we have to make multiple requests in a row in order to implement some functionality. Also, since we end up moving the application state, or the current representation of it, to the client side, it is up to the client to correctly implement the application behavior. We are going to discuss this in more depth in the future lessons. Our next REST constraint is called the cache constraint, or cacheable, and it states that every API response has to be marked as cacheable or not so that the client knows what it can do with it. We're going to discuss how to implement this in practice in the advanced concerns section of this course, but for now, just understand that when we send a response back to the client, we have to explicitly mark it as cacheable or non-cacheable. There is a set of standardized HTTP response headers that we can use to control this. One of them is called the cache header, and there are also the last modified headers, the age header, the expiration header, which can all be used to implement this functionality. The goal of the cache constraint is to improve the network efficiency because there is no need to send another network request if we already have data available locally from a cache. However, the trade-off with caching is that we may end up showing stale data on the client if we aren't aware that there was a change made on the server. The next constraint is the uniform interface constraint, which deals with how components inside of a RESTful system can communicate. And the essence is that the interface between components is generalized. What I mean by this is that information is transferred in a standardized form rather than one which is specific to an application's needs. Now, if we compare this to something like a GraphQL API, where the client specifies a GraphQL query to retrieve the specific information they are interested in. With REST, we are returning a standardized form or representation of a resource back to the client, and the downside is that it may not be specific to the application's needs. Now, there are ways to go about this, and we're going to discuss them in our next chapter when we actually implement some basic functionality inside of the RESTful API. So even though this constraint simplifies our architecture, the downside is that we do have reduced efficiency because we aren't serving the client's need in the most specific way possible.